Hey, my name is Matt Starling. I'm a Wi-Fi engineer and I work for a company called Natilic inside of the UK. I'm also an iscci instructor as well as the co-host of the Wi-Fi Ninjas podcast. I am super excited to be one of the speakers at the Ekahau WiFi Day 2021. How about you, Mac?
Thank you, Matt. I'm Mac Dering, CWNE, ECSC trainer, Wi-Fi engineer at Natilic and co-host of the Wi-Fi Ninjas, and I'm so extremely delighted to be here at Ekahau Wi-Fi Day 2021 that I'm about to do a baby backflip like right now.
The venue type that we can see here is a very large enterprise carpeted office space. They are based out of central London and they also have several floors but a massive atrium that runs through 5 of these floors. The restricted access to the ceiling and the aesthetics were a huge concern when it came to this Wi-Fi deployment, but most importantly what they have at this site is amazing, great coffee which every Wi-Fi engineer needs when they go on site.
The office comes with some unusual perks like a staircase in the atrium, where they're both massive, both the staircase and the atrium, and it's also animals friendly. Even zebras might be connected these days. Additionally, we have tons of open spaces with a lot of users around and potentially a lot of devices, so tons of capacity requirements from the access points that will be mounted in the industrial open ceiling that has tons of metal around. And lastly, we have a beautiful, amazing rooftop with herbs on that you can graze on if you ever get hungry.
What challenges did we need to overcome with the Wi-Fi on at this office then? Well, there was 3 main challenges we needed to overcome. The first one was regarding coverage. The next was capacity, and then the third one was around roaming. So with this office, we have very large office space across multiple floors. That's indoors as well as outdoor space. But what's quite a big challenge to this office was the fact that we've got a large atrium that runs throughout multiple floors. So what we're seeing is a lot of client devices roaming between floors. And also what was happening with the Wi-Fi clients when they're roaming from one floor to an access point that's on the floor either 2 or 3 floors above, they were doing what's called a layer 3 roam, which was taking quite a long time. So if you were using a voice or a video call, you would be having delays or drops in that connection.
It's a beautiful weather now in England. Sometimes it happens, not too often, but it's not too bad today.
Okay, so Mac, I have a question for you. How do you see the Wi-Fi networks being used and utilised when people come back to work post-COVID? And what will be the benefits of having a properly designed wireless network for the users?
Okay, so first of all, I don't see Wi-Fi because it operates in the RF space, but the way that they use Wi-Fi, it will be absolutely different now than it used to be 1 or 2 years ago before the COVID happened, because we will have to maintain the communication between the colleagues working from the office and from home, and tons of them will be working from home, so video and voice will be of utmost importance. So not only we have to make sure that there is a capacity to connect all the devices like mobile phones and tablets and corporate issued laptops, but also we have to make sure that they roam very quickly and efficiently at the same time.
It's extremely important that we ask the customer the relevant questions before we even get to the design phase or stage of going on site. Because if you ask the customer, what are they going to be expecting to use the Wi-Fi for, and they say, I'm going to be using voice over wireless, or I want to use just data only, that's going to impact your design. And it's really important that we capture this in the form of documentation so we have something to reference to later on once we've done our design, our implementation. We use a Wi-Fi questionnaire that we will send to the customer, ask them a whole bunch of questions around what they expect from the wireless, what devices they're going to be using so we can capture the make and the model so we can check their capabilities. And then we can run through this with them on a call. But like I said, it's extremely important that we capture this information because we could then, once we've done our install, we can then go back and we have something to go back and say, this is what we were designing for. What we understand now for the requirements for this Wi-Fi network is that they need to have good voice and video calls over Wi-Fi. So how do we translate that into what we need from our actual Wi-Fi network requirements? Well, we're going to need to have really good primary coverage from our access points, but we're also going to need to have good secondary coverage from our access points. Why do we need good secondary coverage from our access points? This is so that when our client devices roam from one access point to another access point, they will have smooth transitioning from one AP to another. If we do not have good secondary coverage, then our access points are not going to have a good time when roaming. Another thing that we needed to ensure and make was as best as possible was to keep the amount of code channel interference to a minimum. But we also have to be realistic when it comes to large enterprise office spaces where there's multi-tenants and there's a big atrium that runs through the middle. So we want to keep it as low as possible, but be realistic with what we're going to see here. We also want to have a good signal to noise ratio of at least 25 dBs. And as well, we want to keep the channel utilization to below 20% to ensure we have the good quality voice calls over Wi-Fi.
Let's talk some capacity. So we know how many users are going to be on site. We know exactly what types of devices they are going to be using and what applications they are going to be using on these devices, because we've asked all these questions as part of the initial questionnaire data gathering. So having all these details, we should be able to quite accurately scope the capacity needs. I say quite accurately because it's not possible to scope it perfectly. It's such a dynamic model, you won't be able to do it perfectly. What it is instead, what it should be like an educated guess that is based on the requirements, your experience, and your gut feeling that will give you a better value. A common mistake is to overscope your capacity requirements. Let's try to imagine that you are designing for an office with capacity of 100 users. And when you ask your client how many devices every user is going to carry with them, they will tell you typically like 2, 3, or 4. So for this 100 users, you might already be designing for 200, 300, or 400 devices. And then when you start calculating how much data these devices need to work on Wi-Fi network flawlessly, you might start calculating like web browsing, 0.5 meg, video conferencing, 2 megabits per second, streaming of video, YouTube or Netflix, 2 or 4 megabits per second. If you start adding all these things up, you might conclude that you need to cater for 300 devices, 8 megs each. And this will give you like a very heavy, high density design that might not be required. Now take a look at it from a more practical perspective. Okay, we have 100 users and all of them, they're carrying 3 devices per person. But out of these 3 devices, how many are associated to a Wi-Fi network? 2? Okay. So we're down to 200 devices. Out of these 2 devices associated to the Wi-Fi network, how many of them are actively being used? 1? Fine, we are down to 100 devices. Out of this 1 actively used device per person, how many devices are consecutively used in this Wi-Fi network? Every second one, maybe. So we are down to 50 devices, this kind of stuff. And now let's take a look at the applications. So we want to be able to do all of it, okay? Web browsing, file transfers, video streaming, voice and video conferences. But how many of these apps we are going to be using simultaneously? 1, 2. Typical office flow, it looks like this. You have a conference application running like Teams or WebEx or Slack or whatever you are using there, with some sporadic browsing, and maybe you'll be listening to music, and maybe you will sometimes be streaming something from YouTube for work purposes, of course. But actually, instead of talking about it, let's take a look at the real data usage.
Mac, we are currently on a high definition video call over Zoom. What is your current network utilization?
As you can see on the screen, it's extremely high. It peaks at around 100 kilobytes per second, which translates to 800 kilobits per second, which is less than 1 megabit per second. Just as a comparison, my computer is now sitting on 573 megabits per second data rate, MCS 11, Wi-Fi 6, 40 megahertz channel, 2 special streams, and I'm using just a fraction of that, okay? 0.8, with a high definition screen sharing, voice and video over Zoom, with some communicators running in the background. I'm not exceeding even 1 meg of utilization. Up and down, I have 25, 26 KB, which is nothing. Let me go and to the Safari and open a website of my choice, which is Wi-Fi Ninjas. I've just opened it now. We couldn't even see that in the network graph because it's so lightweight and fast. So that's it, guys. That's the real utilization of the network using Wi-Fi in a normal workflow.
So how do we survey for this large enterprise office space? What do we do? What do we use? Well, of course, we use our favorite Wi-Fi survey tool, and that is, of course, Ekahau. But what actually do we use inside of Ekahau, and how do we do it? Well, Ekahau, we use the software, we can use the Pro software on the laptop, or now, with more recently, we can actually use iOS devices to capture our surveys. And for me, this was a massive bonus because I no longer now need to carry around a big heavy laptop with lots of dongles sticking out to capture these capture our surveys. So what do I do? What do I use? How do I do it? Recently, I have been using my iPhone and I've been using a survey feature called Autopilot. What is Autopilot? Well, Autopilot uses the built-in AR kit on the iOS device and it will automatically draw your survey path for you. One big tip though, if you are going to use Autopilot, it's really important when you first start your Autopilot survey that you calibrate the floor plan properly when you're setting your reference point. So you typically want to leave a bit of a bigger distance and ensure you do it accurately. Another really popular survey mode that I use when I use my iPad is the continuous survey mode. So I would be using that where I'll be clicking on the floor plan, scrolling, telling Ekahau where I am, and the rule here is that you click when you start, you click when you turn, and you click when you stop. And you want to keep a continuous pace. You don't want to start really fast and then go really slow. You want to walk at a very continuous pace. And then finally, the last survey mode inside of Ekahau that we can use inside a carpeted office space like this is the stop and go. And typically we probably don't want to use the stop and go survey feature when we're in this kind of environment because we're actually throwing away data when we use stop and go. So stop and go we would typically use if we're in a harsh or a dangerous environment where we can't continuously capture that survey information.
Let's talk about the design. So what is the goal of the design? And the goal of the design is to provide spotless coverage and capacity without contributing too much to channel contention, CCI, channel overlapping. There are several factors that can affect negatively our capacity. The most important one is the design itself. You cannot fix a bad design with good configuration. No. And then you have a CCI, channel contention, channel overlapping, number one killing factor in the wild, seen out there. You also have OBSS, overlapping basic service set, is not as frequently seen, but if you have it, then it will kill your performance quite badly. Non-Wi-Fi interference, if you have it, it will kill your performance quite badly. And lastly, there is a configuration part. If configuration is bad, no matter what you do, your Wi-Fi will also be bad. Let's start with the design best practices. My favorite tip is to cover what you want without covering what you don't want, meaning if you need to, use directional antennas. In a typical carpeted office space, you probably would use omnidirectional built-in antennas because these are most aesthetically pleasing, cheapest, easiest to design for, easiest to mount, and readily available. So let's say that we have an office with 120 users in, like you can see here or here, I don't know. And most of these users, they have one or two devices, typical workflow, voice and video, sometimes some of them cabled in. You might be just fine with using these omnidirectionals every 15-ish meters, so you would have like 6 APs and it feels good, okay? But what if you had crazy users, wireless first, you know that they are super heavy users on Wi-Fi, you understand the requirements, what then? Would you just add more access points, omnidirectionals around? Not really. Typically, it will create more issues than it solves. So you want to have a good frequency reuse. You want to ensure that users are roaming between the access points. And with Omnis, every access point will cover pretty much entire space. So you might want to take a look at the directionals and have patch antennas suspended on the conduit bracket from the ceiling, not too high, like 2.5 meters above the ground, pointing directly down, creating a beautiful cone of coverage. So when you have users moving around, they will be jumping between the radios because they will not be covering entire floor each. Next tip, design for LCMI, least capable, most important device. You must understand exactly what devices you are designing for, and in carpeted office space, typically it would be a mobile phone running voice and video applications. Another tip, stick to 40 MHz until you cannot. If you can use bonded 40 MHz channels on 5 GHz without contributing to CCI, without having too much contention, use it by all means. If your contention is too excessive, just stick to 20 MHz. Mega impactful tip, stick to 5 gigahertz only, especially for your corporate traffic. 2.4 gigahertz typically is dead even without your devices on it. 2.4 gig travels quite long distances. It has just 3 non-overlapping channels. It has tons of non-Wi-Fi but still wireless devices operating in the same band, and then you will have quite a lot of neighbors in multi-tenant buildings with some buildings around you, your neighbors, so don't. But when you are designing for 5 gigahertz, make sure that you can use all available channels, check against DFS activity, check against what channels are available on your access points, and most importantly, check what your clients are capable of, because some of them might not support all 5 gigahertz channels. And lastly, be mindful of how DFS channels work. Your client won't be able to probe actively for the next best AP that it wants to roam to. It will have to listen passively for beacons from the APs before it decides to join that AP. Another great tip is to limit your maximum transmitting power levels. You don't want your APs to be blasting at full power. They will cover way too much. Ideally, you want to match the TX power of your devices, and you don't want to go too low, because if you go too low, it will affect negatively the SNR and modulation scheme used, and therefore maximum speed that you can achieve will also be reduced. Sticking to around 25 milliwatts is typically all right. Additionally, disable lowest available data rates. You don't want to allow them to be too low, because all your management and control traffic will be sent at the lowest basic data rate. Typical rule of thumb is to stick to 12. You can't go wrong with that. Or if it's a higher density, 24 is what we do. Understand the space you are designing for extremely well before you even start the design process. You need to ensure that you know the attenuation of the walls and ceilings, that you know and understand the flow of users, where they work from, how many of them, what are the special areas, high density areas, auditoriums, theaters, town hall meetings, massive meeting rooms. All of it will affect your design. Lastly, make sure to mount the APs and antennas correctly using correct types of brackets. Omnidirectional APs typically in the office space will go under the false ceiling, not behind it, and they will be mounted horizontally, not like a clock. You might have a valid use case when you want to cover a staircase, then you will mount it vertically, but typically they will be mounted horizontally. If you have abstractions around your AP or antenna, suspend it down using conduit bracket, making sure that it's under the level of the abstractions. Let's see if Matt approves.
If you're a Wi-Fi girl or a Wi-Fi guy, you've probably implemented and designed some Wi-Fi networks before. You usually get to a situation in the design or the deployment phase where you'll get pushback from building architects because they don't want you to install these lovely, beautiful access points below the ceiling. They want to put these access points above the ceiling so people can't see them because they get offended by how they look. My argument when I have this conversation with building architects is, okay, fine, put our access points up there, but put those smoke detectors up there as well. And you always see the look on their faces like, what? Of course we're not going to put a smoke detector above the full ceiling. It works over the air. How is it going to detect smoke as well? Well, your answer is it will detect smoke, but just not as good. It's the same with our Wi-Fi, right? You put the access points above the ceiling, yeah, it's going to work, but it's not going to work as well. So try to imagine in this situation where we've got a beautiful office with these industrial exposed ceilings, where there's filled with metal, piping, air conditioning units. If we had installed these access points directly to the ceiling, with all of these obstructions directly around the access point, is it going to work as well? No, but it would still work. So what do we do instead? Well, we have to get some form of pole or conduit to suspend the access point from the ceiling to be away and beneath these obstructions.
Thank you very much for sharing your amazing, insightful tips, Matt. We are eternally grateful. Now, let's talk about CCI and OBSS. Bad configuration and bad design might cause high CCI. Bad configuration or naughty neighbors can add OBSS to your CCI. Generally speaking, only one device will talk at any given time on any single channel. With high CCI, we have high contention. With high OBSS, we have less airtime available to us due to massive amount of collisions. What is CCI? It's also called channel contention or channel overlapping. It describes the number of radios with their cells overlapping with around neg 85 dBm or higher. And it doesn't matter if the access points with the radios on the same channels are yours or your neighbors or neighbors of your neighbors, CCI is CCI. For as long as your APs or your clients, they hear each other, you have CCI. And the more CCI you have, the more contention and the more collisions you're going to see in your network. On top of CCI, you can also have OBSS, Overlapping Basic Service Set. And man, it sucks. Okay, it will degrade the performance of your network even further because now you have overlapping of primary channel with non-primary channel. And what it means is that all the control and management traffic, all the clear channel assessment before the device transmits data is being done on a primary channel. So if you have like a bonded channel of 36 plus 40, whatever, all the checks are being done on channel 36. If you have overlapping on channel 40, so someone being on, let's say, channel 40 at 20 megahertz, both radios will be transmitting on top of each other without, contending for the airtime, and therefore creating even more collisions. And it's really, really bad. What is the impact of the CCI and OBSS in the real world? We've checked exactly that. So we've run a few tests in a lab environment. We have 2 iPhone 12 Pros, 2 Mist AP12 access points, 2 iPerf free servers running on my Windows box. iPhone 1 is connected to AP1, iPhone 2 is connected to AP2, and I wasn't sure if my iPhones are using 1 or 2 special streams. I've seen them using 1, even though they're capable of using 2 special streams. So checked that in the captures that you can see now here. Concluded that both iPhones, they are using 2 special streams. They are associated to my APs on 40 megahertz channels, Wi-Fi 5, SGI shortguard interval, and they are sitting in MCS 8, achieving 360 megs rate, even though they should be sitting, I think, on MCS 9, achieving 400 megs. Not sure why they are doing that. And the channels that we are using for these tests are extremely clean, not used by me nor my neighbors. And from the RF perspective, they are perfectly clean. We have done 3 tests. In test 1, we had both iPhones connected to their own access points sitting on non-overlapping channels, AP1 on channel 124 at 40 megahertz, AP2 at channel 149 at 40 megahertz. And as expected, both iPhones, they were achieving close to 300 megs. It was exactly 274 megabits throughput out of their maximum theoretical 360 megs data rate. In the second test, we've introduced some CCI. Both access points are now sitting on channel 124 at 40 megahertz, and we have 2 iPhones contending for the same airtime, and therefore we would expect to see around half of the throughput when compared to what they achieved in the previous test with no contention. And that's exactly what we see here. They are both getting around 142 megs, which aggregated together gives us the same result as a single iPhone in the previous test with no contention. If we start adding more and more devices, we will also start adding more and more collisions, and therefore the aggregated throughput of these multiple devices will start getting less and less than the maximum achievable throughput from a single device with no contention. In the last test, we've introduced cheekily some OBSS. So the first access point is sitting on channel 124 at 40 megahertz, and the second access point is sitting on channel 128 at 20 megahertz. So the second access point is overlapping with the first AP on its non-primary channel, meaning when you have both devices associated to both access points, they will both be talking at the same time, one over each other, without playing the game nicely. They will not be contending for the airtime. They will be shouting one on top of the other. So the result that they are getting now is considerably worse than in a previous test. We still have a CCI of 2, but with OBSS on top of it. And now we are down to 119 megabits per second per device. Back to you, Matt. Let's take a look at how to do the surveys and design.
When designing for the typical carpeted office environment, we probably wouldn't use the pre-deployment AP on a stick type survey too often, just like what I've got set up behind me. Well, why is that? That's because we only rely on this type of survey when we cannot accurately predict how the RF is going to behave in the environment in our predictive model inside of Ekahau. Designing for our predictive model inside of Ekahau, Now this is where it gets really important that we capture the right accurate information. There's two elements to your predictive model. Well, there should be anyway. There should be an on-site element and an off-site element. So let's first tackle the on-site element. What's the first thing that we're going to do when we go on site? Well, it's going to be a visual check. We're going to get someone to show us around so we can take lots of notes, lots of pictures. Start looking at the ceiling heights. Are there any obstructions? What type of ceilings? Are we going to be able to mount directly to the ceiling? Are we going to need a suspended pole? Are we going to need some sort of enclosure? Or is there no way we can mount to the ceiling and we might have to put the AP on the wall, but then use a bracket to make it horizontal still? What about DFS? How do we know if we can use those additional 5 GHz channels to give us that extra bandwidth? Well, if it's a greenfield site and there's no wireless equipment there currently, we're going to have to take our own mobile survey equipment so we can check logs for any radar activity. But if there is an existing wireless infrastructure there, we could probably just check the logs of the current infrastructure to see how heavily impacted the site is by DFS and then make a decision on whether we want to use these channels or not. Measuring attenuation. One of my favorite sayings with Ekahau is garbage in, garbage out. If we put bad information into Ekahau, well, guess what? You're going to get bad information out. This is why it's crucial that when we go on site and we measure attenuation of the types of material that's going to be on site, like the walls, the doors, the windows, we do it accurately. Because if we put the wrong values inside of Ekahau, our predictive design will therefore be wrong. And then when we deploy our access points, our coverage isn't going to be what's expected. So how do we accurately take wall attenuation measurements whilst we're on site? Well, we're going to need to have a test Wi-Fi device. This can be your access point or a travel router, whatever it is, I do not mind. But what we need to ensure is that the test device is at least 5 meters away from the wall that we want to take the wall attenuation measurements of. Well, why is this? This is because of free space path loss and the inverse square law. If the test device is at a closer distance, we will see a huge fluctuation in the signal strength without there even being a wall there, that it will be impossible to get the correct wall attenuation measurements of that wall. So once our device is now 5 meters away from our wall that we want to take the measurements of, we can stand there with our Ekahau Sidekick and our analyzer app. We can read the measurements from our test device, and then what we're going to do is we're going to go onto the other side of the wall, but make sure we stand in the same way. So if the Sidekick was on your left hand side, on the other side of the wall, when you come to this side of the wall, ensure that your Sidekick is also on your left hand side and you're in roughly the same position, so we can get accurate wall attenuation measurement details for the wall, and then we can take that information and we can go and update our predictive design in Ekahau with the correct values. And the final part of the on-site element is that we want to understand the current RF environment. And we can do this by doing a quick validation survey. We are now ready for the best part of designing Wi-Fi networks, building our predictive model inside of Ekahau. So let's take a look. Here we can see we've got our Ekahau project file loaded in with a floor plan from the site. The first thing that we have to do when we load a floor plan into Ekahau is give it a scale. When we go on site, we use a laser measure to measure 2 distances from one point to another on the floor plan, so we can give Ekahau an accurate scale of that floor plan. So what we do now, if I grab my scale tool and I zoom in, we measure the distance between these 2 pillars. So if I click and drag my mouse across, I can see the distance between here was 8.6 meters, which we validated on site by using our laser measure tool. If we are off by 20 centimeters in the first 1 meter for the scale of the floor plan, it might not sound like too much, but if you have a floor plan that scales for over 100 meters, that 20 centimeters now turns into 20 meters, so the accuracy of our predictive model will now not be very good because we've not got a correct scale. So that's why it's super important that we accurately scale our floor plans inside of Ekahau. As this is a multi-floored office, we need to tell Ekahau that we want to create a 3D building inside of our Ekahau file. So what we need to do is create a building, add the floors, and then we need to find something that aligns vertically across these floors. So I grab my floor alignment point, and what I've used here is the lift. The lift runs between all of the floors, so I've used these as my alignment points. If I open up over here, we can see I've created a building and added all of the floors, and I get a green OK to tell me that my floors are all aligned vertically. So I'm now ready to see my predictive design simulated across multiple floors. I'm now ready to start drawing attenuation across my floor plan. The first type of attenuation that I'm going to use is the walls. And what I'm going to do is use the data that I captured on site from my wall measurement attenuation testing to make sure that the wall values match what I captured on site. So inside of Ekahau, underneath the planning tab, if I select the wall option, you can see that I have drawn multiple different walls across the floor plan, ranging from concrete walls around the core of the building to drywall and interior grass around where the meeting rooms are. But one type of wall that I want to draw your attention to is around the atrium. This wall does not go from the ground to the ceiling, it only comes up halfway. So this could be known as a pony wall. So what I've done inside of Ekahau is I've created my own wall. And I've said, hey Ekahau, this wall only comes up to 1.5 meters. So Ekahau now knows that this wall doesn't go from the ground to the ceiling. So when it's doing its calculations, it can use that data to make our simulation as accurate as possible. Remember, garbage in, garbage out. Let's take a look at the next type of attenuation we can configure inside of Ekahau. So underneath where I've got the wall option, I'm going to select the rectangular attenuation area. And what we can see is there's a lot going on now, but if I just zoom into this area, we can see that I have drawn and configured attenuation areas for the lifts, for the lockers, for the cabinets, and for where people will be sitting. This is so that Ekahau can take into calculation these types of attenuation areas. Now that we have defined our attenuation on the floor plan, I have just hidden it so we can see the floor plan a bit easier. We need to tell Ekahau where we do and we don't want coverage on the floor plan. And we do this by defining what's called as areas. So if I select the area tool now, you can see that I've drawn two coverage areas, one for inside and one for outside. And inside of the areas, we can define the requirements. So for the coverage requirements, you can create a coverage profile, which I have done. And you can also include capacity details. So how many devices are going to be using the area and what applications and what SLA they need to have. If we want to tell Ekahau that there's parts of the floor plan that are not in scope, we then define exclusion areas. So I have done that for where the core of the building is, and we do not need to have coverage here. Let's take a look for the first time now where and why we have placed our access points how we have in our predictive design. We have taken into consideration where we can and where we cannot mount our access points, how the Wi-Fi network is going to be used, and what devices are going to be using the Wi-Fi. Taking all of this into consideration, we came up with a design that meets the coverage requirements as well as the capacity requirements. Our design was primarily focused on 5 GHz, using 20 MHz wide only channels, and on our access points for the 2.4 GHz, we had to disable multiple radios so that we did not cause too much co-channel interference on our own Wi-Fi network. Now that we have completed our predictive design inside of Ekahau, we are ready to run a report to provide to the customer and the installation team. You can either use the one-click report that's built into Ekahau, or you can create your own custom report templates. We use our own custom report templates, and we then provide that to the customer to give a detailed report of what we have done on-site and off-site. And we also give really clear and easy instructions to the installation team for how we want our access points mounted and make sure it's easy for them to follow.
So Matt, how do we design for these beautiful, vast, open spaces and terraces outdoors?
Well, in Wi-Fi there's a saying, designing for coverage is easy, but what we needed to do here is not just think about the coverage.
Is that a saying?
Have you not heard it?
Doesn't it have any more depth than that?
What else is it?
I don't know. In this rooftop, you could probably cover entire space with just one access point, positioned 4-5 meters above the ground on the wall quite high up on my right hand side. But instead, we know that we have tons of events here. We've opted to choose 4 APs, like the access point here, positioned slightly closer to the ground, so they do not cover as much. And by doing it, we are reusing the frequency in a way where we will have more capacity in this lovely space.
So Mac, we have got a massive atrium that runs through multiple floors of this office. What did we do to overcome the challenges around Wi-Fi and atriums here?
So obviously the atrium is not the only massive thing here, but when it comes to the design of Wi-Fi around the atrium, there are multiple best practices that you can follow. First of which is to put access points slightly farther away from the atrium to minimize the CCI. And additionally, if you want to minimize the roaming, cross-floor roaming between the floors, you want to position this AP so they are in line, okay, not scattered around. If they are scattered around, you are maximizing risk of cross-floor roaming. You don't want that. And if you really want to be very detailed about that, and if you want to make sure that your roaming is extremely spotless, you might want to position directional antennas pointing towards the office outside from the atrium. Beautiful stuff. So we have a good roaming. Your devices, they are associated to the access point on the floor that they are on. What's next? How do you make sure that it's fast and beautiful?
Yeah, great question, Mac. So what we did here is we actually used the optimized roaming amendments available to us in Wi-Fi. So what we used is we used 802.11r, 802.11k, and 802.11v. All of these amendments, they're going to help our devices roam quicker when they go from access point to access point. Tip here is you can't just blindly enable these amendments on your SSIDs without checking if your client device support them. Because if your client device doesn't support one of these amendments, they're either not going to be able to associate to the SSID or they're going to be having connection issues. So what did we do, Mac, to ensure that our Wi-Fi clients not only support this, but they actually support these and work very well?
And that's the last tip of the day, and a very important one. When you've designed your network to be voice and video network for the LCMI, least capable, most important device, that in this office was the phone issued by the company running a soft voice video client, you want to jump on the conversation, jump on the video conference call, and walk around the building making sure that it's spotless, fast, and amazing. And also, don't try to troubleshoot issues that are not there. So if you want to check your roaming with a MacBook, you won't be able to, because MacBooks, they are not designed to roam quickly. They are designed to open it up, connect to the Wi-Fi, close it, move to the meeting room, open it up again, and they will connect to the best AP. And that's it.
Great tips.
Amazing tips. And man, this is identical.